Before we get started, are there any questions over the homework assignments? So, what we're looking at today is more properties, or starting to really start digging into some of the properties of logarithms. I've talked about this before. I've mentioned the fact that logarithmics and exponentials are inverses of each other. So a logarithmic and the exponential form of that logarithmic will be inverses of each other. They undo each other. And one of the nice things with that is that if we have log base b of b to the x, it will simplify to just x. It will simplify to that exponent. And we'll get into more of why that works, especially tomorrow. It's kind of stemming from the fact that our exponential properties, our exponent properties of logarithms, says we can move that exponent to the front. We can move it in front of the log. And log base b of b is 1. So we just get that exponent. The other nice thing, b to the log base b, if the base and the base of the logarithm are the exact same, what we have left is what's inside the log. They simplify each other out. Because they're inverses of each other, they're undoing what the other one does. So, if we take that understanding and look at 10 to the log of 4, this will simplify. Because log of 4, even though the base is not written, it's understood to be 10. It's understood to be 10. So we have 10 to the log base 10 of 4. Since the base and the base of the log are the same, this is going to simplify to 4. It will simplify to what's inside the log. And the interesting thing is I can go 10 to the log of 4, and because it's all numbers, the calculator will tell us it is indeed 4. Questions on this here? Our second one is log base 5 of 25 to the x. Now this would simplify and this would reduce nicely if we didn't have 25 but we had 5. Well, we can actually rewrite 25. Because 25 can be written as 5 to a power. 5 times itself, how many times is 25? Twice, yes? Because 5 squared is 25. So we get this in a form where the base and what's inside are the same. They match up. We have that base of 5 and what's inside the log is 5. Now, unfortunately, it's just, we could try to start simplifying at this point, but we have a power of a power, so let's reduce it first. Now, powers of powers multiply. So we have log base 5 of 5 to the 2x. Powers of powers multiply. So that 2 and x would multiply together to give us log base 5 of 5 to the 2x. What do we think this would reduce to? X, it would reduce to that exponent. Because log base 5 of 5 is 1, and we'll get into it tomorrow with our properties of exponents and logarithms. That exponent we can throw to the front. So it's really 2x times log base 5 of 5. Log base 5 of 5 is 1, so it's just 2x. And this is going to be very helpful, especially once we start solving to be able to get stuff out of the exponent and be able to start working with it and solving. Questions on these here? Next one we're looking at is 10 to the log of 18. 18. Because the base is understood to be 10 for that log, we've got 10 to the log base 10 of 18. The base and the base of the logarithm are the same. So this reduces to 18. As much as we want to say that the next one is just x, we cannot, because the base of the log and what's inside are not the same. Because for us to be able to reduce these out, to cancel these out, what I really need is for what's inside that log to also be a 4. Because log base 4 of 4 would reduce. Log base 4 of 16 does not. So what we need to do to get it to reduce is rewrite 16 as 4 to a power. And 4 to what power is 16? Yes? So really all we're doing here is just manipulating this, rewriting it so we get this base, the base of the log, and what's inside to be the same. And this would best be 2x. Our log base 4 of 4 simplifies, leaving us with that exponent of 2x. Questions on this here? Are you ready for the next one? 8 to the log base 8 of x. Would be? Wouldn't be 8. It'd just be x, because the base and the base of the logarithm are the same. They cancel out, leaving us with what's inside the log as x. They reduce out. Because those two match up, they reduce, they simplify down. Questions on this here? Questions on anything we've done so far? Let's look at the next one. Log base 7 of 7 to the negative 3x. Well, the base of the log and the number inside are the same, yes? So we should be left with the exponent, which is so it simplifies to negative 3x. We good? It feels like there should be more to this than this. It shouldn't be this nice, but it really is. And especially once we get solving, this is going to make the process nicer, to be able to solve these here. Log base 2 of 64 to the x. Unfortunately, it's not x. Because the base is 2, and the number inside is not 2. Because we need it as 2 to a power. Because 2 to the 6 is indeed 64. Yes. Powers of powers multiply. So our 6 and x multiply together to give us the 6x. Log base 2 of 2 will simplify, leaving us with that exponent of 6x. Questions on this here? Now we get to this last one. E to the natural log of 20. What is the base of a natural log? It's understood to be e. So we really have e to the natural log base e of 20. So this would be 20. Because the big difference between log and ln is that the base is e. That's really the only difference between the two. They're still logarithmic functions, We just write L in to say, hey, the base is E. That's really all the L in is signifying. It's still a logarithm, still works the exact same way. It is the same thing, but the base is E. It's just understood. Questions on these here? Now, there is something nice with this property, because if the base of the log and what's inside are the same, they simplify out, leaving us with the exponent, yes? Let's bring back something that we were working with the other day. B to the x equals y. You don't have to write this down. We're going to look at it. Because what we did yesterday and the day before was rewriting logarithms as exponentials and exponentials as logarithms, yes? So what we said for this here, if we rewrote it, it would be log base b of y equals x for doing our switch. Okay? One thing that we can do with logarithms is we can apply a log to both sides. It's just an operation. So if I apply log base b to the left-hand side, we get log base b of b to the x. Well, log base b of b will simplify. And it will leave us with x equals. What I do to one side, I have to do to the other. And when I apply log base b to y, we get x is equal to log base b of. Isn't that the same thing we got when we did the switching from one to the other the last 2 days? That's essentially what we're doing. That is the exact same process as what we're doing. This here is a more written out version where we can see what's switching, what's taking place. I'm not having to make sure I know what's taking the place of x, y, and b. We apply it to both sides to get it produced. Now the question comes, well, what do I do to pick the value of b? How do I know what value of b to pick? Well, we want this b to go away, yes? And for it to go away, this value of b has to match it. They have to be the same, yes? So whatever that value of b is that we're starting with, that's what we're going to put the base of the log to. So we get those two to be the. Now the question is, could we go the other direction? Could I start with log base b of x equals y and get it to exponential? Because what we also covered just a few minutes ago, if the base of what we have a log to is the same. So if I put this and make this b to the log base b of x, I put that essentially in an exponential form. I put it to the power of b, or put the log base b to the power of b. Words. These are now the same, yes? So that left-hand side would reduce to what? X equals. Well, what I do to one side, I have to do to the other. So it's telling me x is equal to b to the, which is the exact same switch we did the other day, yes? Same thing, same process. Works just as well, yes? We good with this here? Now, the only reason I would say doing this is better than just switching from one to the other is when we hit inequalities. Equations, order or sides that we have it on does not matter. Equality, both are equal. We can flip one side or the other. Inequalities, what's on what side matters, because one's going to be greater than the other. This, that's what we did on the last two. Make sure that we don't have to check and make sure we have the things on the right side. But we will get more into that as we get going, especially with solving. Because when we look at these here, this is really finding inverses, the last part of 6.3 that we're going to do. And it seems like there should be a big process, a big thing going on with this here. So there's a few main steps. First step. rewrite f of x as y. We want to rewrite f of x as y. That's the first step in finding the inverse, because logarithmics, exponentials are inverses of each other. So we're finding the inverse. Now I will say this, if it does not give us it in f of x form, b, we don't have f of x, we just have y, we ignore step 1. We don't have to change it. But this also means because we started out in function notation for a, we have to end in function notation. If we start off with f of x, we're going to need it at the end. It's not that bad, it's just going to be rewriting y as f inverse. Step 2. Switch x and y. Switch x and y. Everything else about the function is going to stay the same. We're still going to have the 6, but instead of it being to the x power, it's going to be to the y power. Instead of having y equals, we're going to have x equals. We just flip the x and y. We flip the input-output. Step 3, most parts, even though it is just 3 words, solve for y, we need to get y by itself. We need to get y by itself. So we're going to have to, it seems like we can do addition, subtraction, but we're going to have to switch it from exponential to logarithmic. So we can do the switch. We'll do the first 2 here with just switching from exponential to logarithmic like we just did, like we did yesterday and the day before. Then we'll do a few where we actually apply the log and exponentials to it.
Rachel, come to the office, please.
So if we did the switch as we did before, changing this from exponential to logarithmic, we'll start off with log because the base is not e, to the base of 6 of x equals, because it's just that switch method we did the other day. Log base b of x equals y if and only if b to the y equals x. Questions on how we switched it to that exponential form, or from exponential to logarithmic, is y by itself. So that undid that function. It got that value of y or y out of the exponent, and y is by itself. And the last thing we have to do is rewrite y as f inverse of x. That -1 power signifies, especially in function notation, that is the inverse of f of x. So we'll rewrite this as f inverse f to the -1 of x equals log base 6 of x. And again, if it did not start off with f of x, we are not ending in f inverse. Since this one started off with f of x as function notation, we needed to end in function notation. Bless you. So if it starts off like the next one with y, we're going to end with y. We're not going to just throw it back in. Questions on this here? Now, one nice thing to know, because the ACT, the full ACT, does have that built-in graphing calculator. So if you do get it, that's great. If not, that's fine. Now, for us here, our starting function was 6 to the x. I graphed it here. This is the graph of it. Now, if you notice, there is that other line I have included, y equals x. inverses are always reflected across this line. So 6 to the x inverse should be a mirrored reflection across the line y equals x. Now we found math log base 6 of x to be the inverse. And if we tell it to graph it, we do see that it's a mirror image across this line. They're reflected across this line, which means they are inverse functions. And this is especially nice to know if you're able to graph both of them, especially during the ACT. It said find the inverse of this here. Or answer choice is yes. So I can graph all 4 and see which one reflects across this line. The one that does is the inverse. The ones that don't are not. Questions on this here? Are you ready for the next one? Y equals the natural log of x plus 3. X plus 3 are inside the parentheses, so they're stuck together. They're pretty much one term. Step number 1, rewrite f of x as y. Well, does it have f of x? No, so we're going to skip that step. It also means we're going to skip step 4. If it does not start in function notation, we're not ending in function notation. So really the first thing we're going to do is switch x and y. So we get x equals the natural log of y plus 3. Now we can do the switching method to solve for y, to get y by itself. We're trying to get that y out of the log by switching it to an exponential. Since it's a logarithmic, the base is understood to be e. So we have e to what power? It would be to the x. And sometimes, again, it is easy to get them mixed, especially if we have more than one term inside the log, and especially if we have one written as natural log of x equals y. Here we're looking at the x equals natural log y plus 3. It's sometimes easy to get them flipped. So we had e to the x is equal to y plus 3. Is y by itself? No. So we need to get it by itself. And to do that, we can subtract 3 from both sides. 3 and negative 3 cancel, or 3 minus 3 simplify out, leaving us with y equals e to the x and 3, are they like terms? No. So we just get e to the x minus 3. Y is by itself, so we are done. We don't have to write it in function notation because it did not start in function notation. Natural log of x plus 3. This is what we started with, so that's the graph. Natural log of x plus 3. And we said its inverse was e to the x minus 3. We see that they do mirror across this line. It doesn't look like the blue graph continues down. It does continue down farther than what is shown there. It just gets very, very close to this line, x equals negative 3. Questions on this here? Let's look at the next two. F of x equals 11 to the x. First step. Rewrite f of x as y. Then we need to switch the x and y. Telling us x is equal to 11 to the y. Now for this one here, we could do the switching method, try to keep things straight. Let's do what I did just a minute ago with applying logs to both sides. Because we can apply a log to both sides of this equation and achieve the same result. What would the base of this log need to be? Because we want that other side to simplify, yes? We want it to simplify to y, but the only way for it to simplify to y is if the base and the number inside are the same. So we have to have log base 11. Because log base 11 of 11 to the y is indeed y. Because if the base and what's inside are the same number, they reduce out and leave us with the exponent. If there is no exponent, it's going to be 1. Because log base 11 of 11 to the y is y. But that tells us the left-hand side is log base 11 of x. Now, there is a value of x that would make this simplify, and that would be when x is 11, but x could be any other input value, so it doesn't always simplify. Questions on how we got log base 11 of x equals y? Did we start in function notation? We started off with f of x, yes? So that means we need to finish in function notation. So we're going to leave it or finish it with f inverse of x, f to the negative 1 of x. If it doesn't start off in function notation, the homework won't. We can just leave it as y equals. Questions on this here? You ready for the next one? Y equals the natural log of x plus 6. Don't have f of x, so we don't have to switch it to y. So we can go straight to step 2. We switch x and y. So this will tell me that x is equal to the natural log of y plus 6. Now, since we're starting with a logarithm, what we can do, instead of applying a log to both sides, we're going to put these both sides to a base. And that base is going to be the same as whatever the base of the logarithm is. Well, this is a natural log, so the base is understood to be e. So if I put the right-hand side, that natural log to the base e, the natural log and that e will simplify out, leaving the right-hand side as y plus 6. However, I can't do this to one side. We've got to do it to both sides. So tell me the left-hand side is e to the x. Makes the switching step a little bit nicer. Is y by itself. Now we've got that plus 6. So all we got to do is solve it from there. We can subtract 6 from both sides, telling us y is equal to e to the x minus 6. Y is now indeed by itself, so we are done. Questions on this here? It does make the switching a little bit nicer. We're ready for the last two. We need to find the inverse of y equals 4 to the x power. Already in y equals, so the first thing we can do, I'll just rewrite it, is switch the x and y. Now for us to be able to get the y out of the exponent, we're going to have to use logarithms. They're going to undo our exponential function. And we're not going to apply just log of anything. We're going to apply log base what? 4. Because on the right-hand side, log base 4 of 4 to the y is just y. Log base 4 of 4 simplifies. On the left-hand side, we will still have log base 4 of x. Y is by itself. There's nothing else that we have to do. So that's it. If you want to rewrite it or have it so that y is on the left, that is perfectly fine too. We're ready for the last one. We want to find the inverse of y equals the natural log of x minus 5. First thing we need to do is switch x and y. Since we're starting as a logarithmic, we're going to need to get to it or rewrite it as an exponential. And to do that, we're going to put both sides to the base of e. And when we do that, the left-hand side is going to become e to the x. Doesn't simplify, doesn't reduce, it's just e to the x. The right-hand side, the e and the natural log will simplify out, leaving us with what? Y minus 5. Last thing we need to do is get y by itself. So we can add 5 to both sides. Telling us y is equal to e to the x plus 5. Questions on this here? Question on anything so far? We ready for the next one? That's it. 35 through 40 all. And 43 through 49 odd.